So here we need to note down that biomedical signal processing vision techniques to eliminate background noise. Yes, we use this for eliminating the background noise, enhance the signal detection method, because whenever we use a biomedical sensors, the captured signals is not in a good condition, so we have to enhance them. So we need some kind of algorithm to enhance the biomedical signals, and we need to analyze the computer data, making results to easy comprehend and apply. The analysis framework derived from statistical signal processing. The framework treats as random signals. The processing is Pinner filter, Kalman filter, utilize statistical characterization. Denoising techniques are well established. The field of biomedical signal processing continues to expand. Development of various novel biomedical instruments. The advancement of medical imaging technology, MRI, but our focus is only single dimensional signals. So we will not focus on that. Let's go to the next. The trends in biomedical signal feature extraction. Yes, we need signal processing techniques to extract the features from, but what kind of features? Signal analysis involves identifying signals behavior, extracting linear and non-linear properties, compression or expansion. Let's see what a simple plain Google tells us about the biomedical signal. What is a biomedical signal processing? Well, this is a space-time or space-time records of a biological event such as breathing, heart, or contracting muscles. These are the kind of biomedical signals. And the electrical, chemical, and mechanical activity that occurs during these biomedical events often produce signals that can be measured and analyzed. So whenever we measure and analyze the biological events, these are the biomedical signals. So what is the application of biomedical engineering? Well, to extract clinically and biochemically or pharmaceutically relevant information in order to enable or improve the medical diagnosis. Obviously these helps in medical diagnosis. Three type of signal processing: audio signal processing, image and video. These kind of data could be processed. Why are biomedical signals important? That they help to drive only the filtered data and relevant parameters. um, if you have watched the video on my channel about the ECG signal processing, where we denoise the ECG signal, you may have seen how noisy the ECG signal is when first captured, and then we extract the filtered and clean ECG out of it, so it gives us pretty much good information. What are the five biomedical signals? Well, ECG, the amplitude is 2 to 200 microvolts EEG, and the ECG is 5 microvolts, 0.125 microvolts. EMG, it is EMG is dependent on the muscles, and it is 0.125 microvolts as well, similar to the ECG. And then we have EOG, which is 10 to 3500 microvolts. So biosignals, an overview. This is Science Direct about the biosignals. And the data of the biological phenomena that allows describing a system can be of electrical, mechanical, acoustic, thermal, optical nature, and so forth. All of these are referred to as biosignals. Okay, so examples of electrical biosignals. These signals are measured with a differential amplifier. Yeah, this is also very important point, that most of the time the biosignal can be electric or non-electric. The most common of the biosignals are bioelectrical, usually taken to electric currents produced by the sum of electrical potential differences. So most of the time the bioelectrical signals are captured from the specialized tissues, organ or cell systems such as the nervous system. These signals are measured with a differential amplifier, which registers the difference between two electrodes attached to the skin. So the kind of signals we have is let's copy them. How to, like this. Then nope, delete this one. Here we go. Yes, we copy this, then we, the next signal is electrocardiogram. Copy it. Let me record this. Then we have another one, which is ECG. Then we have another one, which is EMG. I know it is kind of sucks. Then we have EGG. Here I like to mention some things that the wavelet transform and useful for non-stationary signals like EEG. The wavelet transform are useful for non-stationary signals where frequency components change over time. So we have to remember that the wavelet transformer will come handy whenever we have such kind of signals which it changes and where frequency components change over time. So we're detecting a specific event such as epileptic seizures, and the variants is continuous wavelet transform and discrete wavelet transform. The PCA is another very popular algorithm which is used for reduce the dimensionality of the data while preserving as much variance as possible. The application is used in EEG, ECG, and EMG data, independent component analysis, and just like the PCA, this is component analysis, but it is independent component analysis which separates mixed signal into statistically independent components. So these are used to remove the artifacts such as eye blink, muscle activity from brain signals. So independent component analysis. Then we have the Kalman filter. It provides an efficient recursive solution for linear dynamic systems. And then we have auto-regressive modeling, which models the time series data by expressing a signal as a linear combination of its previous value. And we have cross correlation and coherence analysis. It measures the degree of similarity between two signals as a function of time or lag. Then we have time frequency distribution. It analyzes the signal's energy distributing over time. And then we have a machine learning, the hidden marker models. The HMM is very popular for modeling system where the state is not directly observable but can be inferred from observable events. So whenever we have some sequence modeling in the biomedical signals, such as detecting the heartbeats in ECG or identifying gate phases in EMG. So the nonlinear dynamic methods, entropy, Bayesian filtering. It provides the probabilistic inference for dynamic systems. It is could be used for noise reduction and real-time tracking of biomedical signals. Empirical mode decomposition. Decompose signals into intrinsic mode functions. R peak detection algorithm, spectral entropy, envelope detection, and Hilbert transform. We use this in a recent video that I had released about the ECG signal. So we use this for QRS complex detection. I like to explore further the Bayesian filtering. The Bayesian filtering is something new for me as well. I haven't seen the Bayesian algorithm in the filtering phase. So paragraph and list 30 uses. Let's see what it says. That it is a probabilistic technique used to estimate the state of dynamic systems by combining prior knowledge with new noisy observation. It works iteratively, updating the belief about the system state as new data become available. Okay, so it is something like when we have a continuous data coming in and we have knowledge of the previous data, then we remove the noise from the new incoming data. I hope so. It's something like that. System state as a new data becomes available using Bayesian theorem in signal processing. Bayesian filtering such as Kalman filter for linear system and the particle filter for nonlinear systems are used to reduce the noise, track signals, and make prediction in real time. The core advantage lies in the ability to continuously improve estimates even with uncertain or incomplete data. It is something Kalman filtering. So maybe the Kalman filter is type of Bayesian filter, maybe, but I'm not sure. Noise reduction in ECG signals. Okay, tracking heart rate variability in real time EEG signal denoising for brain computer interface applications, respiratory rate estimation from noisy biosignals, localizing moving objects in radar signals, speech enhancement, adaptive filtering, motion tracking, reality systems, position tracking in GPS system, seismic signal analysis, noise suppression in EMG signals for prosthetic control, adaptive noise cancellation, weather prediction, object tracking, signal prediction, digitring in real-time video streaming, filtering sensor data, ECG signal feature extraction. Uh, nope, nothing. Let's see what the Google says about that. Bayesian filtering. Okay, so let's explore the image. Odometry base, velocity base. It's not really making sense to me. Hmm. Bayesian filter is an algorithm used in computer science for calculating the probabilities of multiple beliefs to allow a robot to infer its position and orientation. The bias filter is just the probabilistic representation of a system state belief. We can often update this belief to move more accurate. Okay. Kalman filter is a type of Bayesian filter. Let's come to the scholars. Trends. Energy efficient biomedical signal processing. Biomedical signal analysis. Nope, nothing good. Neural networks, noise assisted data processing. Okay. Non-linear Bayesian filtering from Kalman filter to particle filters and beyond. It's taking too long. Just go back. What are most common Bayesian filtering application in biomedical engineering? Studies suggest that the most common Bayesian filtering applications in biomedical engineering are denoising biomedical signals, tracking nonlinear, non-Gaussian dynamics, and reconstructing sparse biomedical signals. Bayesian filtering techniques are widely used in biomedical engineering to estimate the state of a time varying system based on observational data. These methods are particularly useful for handling noise and uncertainty in biomedical signals, making them essential tool in various applications. Key insights: denoising biomedical signals. Bayesian filtering is effectively used to remove cardiac contaminants such as ECG, MCG, and ballistocardiographic artifacts from other biomedical recordings like EEG and EMG, as well as for cancelling maternal cardiac signals from fetal ECG and MCG. Parameter estimation and model selection. Nonlinear non-Gaussian tracking. Particle filter, a type of Bayesian filtering, are used for online tracking for nonlinear and non-Gaussian systems, which is crucial for processing data in real time and adapting to changing the signal characteristics. Bayesian filtering techniques are predominantly used in biomedical engineering for denoising biomedical signals, parameter estimation, and model selection. Okay, let's ask and list most common statistical algorithms. A posteriori clustering, used for noise resistant speech signal processing and classification of biomedical data using neural network and clustering algorithms. Histogram and kernel probability density estimation, method for statistical construction of histogram models and non-parametric probability density estimation with kernel functions. Time series classification. Well, Genetic algorithms. Utilized for simulating correlated binary data in biomedical research, particularly useful for generating high dimensional data. Clustering methods, blind source separation, and independent component analysis. Algorithm for separating multiple signal sources based on their statistical independence used in applications like fetal electrocardiogram extraction and optical imaging for cortical tissues. Fuzzy clustering proposed for biomedical data analysis, offering higher efficiency compared to traditional Bayesian models. So the fuzzy clustering. Then we have random forest decision tree and an SVM. These are all ML algorithms. Hmm. Genetic algorithm. Independent component analysis. I think special topic section on advances in statistical signal processing. Let's see if we have. Uh, can we download? No. How to download this paper? This special issue highlights the potential of statistical signal processing for biomedical applications, offering more accurate source modeling and artifact rejection. Exciting advances are emerging in the field of statistical signal processing that should be brought to the attention of the biomedical engineering community. Several algorithms have been proposed to separate multiple signal sources. Um, Blind source separation and independent component analysis. These two should be paid attention. Fetal electrocardiogram extraction. A practical example of two signals of the same frequency and model but independent sources that appear mixed by recording conditions. The second paper compares several IC algorithms to analyze optical imaging of cortical tissue in order to differentiate normally occurring variations with stimulus driven variations. The third paper studies the autonomic cardiac outflow by separating the effects. So, yes, it is kind of trying to separate mixed signals. One is mixed by default and the other due to some motions. Let's go to the full text of this paper. Okay, it is IEEE and maybe it is not open source. Hmm. We can further search Arduino and biomedical applications. Biomedical instrumentation with Arduino. After biosignal acquisition system based on the Arduino. Okay, what is this? Biosignal acquisition has been a topic of increasingly growing development since it constitutes the basis of diagnostic systems and contributes to a better understanding of the body functions. Nowadays, novel applications of biosignals are emerging in areas where they are not traditionally found, such as the use of electrocardiogram signals for biometric purposes. Therefore, the main objective of our work was to develop a low cost acquisition system capable of capturing vital signals using ECG as a test bed. Okay, uh, they use where the Arduino is used to acquire EEG signal, measure plus detect alcohol levels, and many other examples. Let's see the system architecture. It is only using the ECG sensor, so it is not very popular, I mean useful in our case. Choose Bluetooth, adjacent object containing information, start, acquire, stop, experimental evaluation. No, they are just using the ECG signal, so ECG signal is overdone. Okay, let's back to blind source separation is mostly used with the independent component analysis. So in this chapter we focus the use of independent component analysis in biomedical systems. Several studies dealing with the ICA based biomedical systems have been reported during the last decades. Nevertheless, most of these studies have only explored a limited number of ICA methods, fast ICA and Infomax. In addition, the performance of ICA algorithms for arbitrarily electrophysiological sources is still almost unknown. Okay, this prevents us from choosing the best method for a given application and may limit the role of these methods in biomedical systems. To overcome these limitations, the purpose of our study is to first show the interest of ICA in biomedical applications such as the analysis of human electrophysiological signals. Next, we aim at studying 12 of the most widespread ICA techniques in the signal processing community and identify those that are most appropriate for biomedical signals. I think this will give us more insightful information about the ICA. So the techniques they are talking is Infomax, Fast ICA, or PICA, Meyer Independent, I think mutual information, MI, which is directly related to the definition of independence via the Kullback-Leibler divergence. Alternative algorithm used to normalize the differential entropy, which is special distance. Okay, let's see. So these are the name of the algorithms. Mm-mm. So here may be the information about